G'day again all. Something a little different this time. I'm going to be discussing some of the physics and engineering behind how the Tacx Neos generate their resistance to the power that we all seem to be dropping into these things. A little bit of housekeeping just before I kick off today. Audio quality might not be so great. I'm in the shed again, but you might hear a little bit of ambient noise coming around. So we've already covered what the internals of a Tacx Neo look like. They're very simple, not many moving parts within these. A whole heap of stators here, or a whole heap of phase poles wrapped in copper wire, 30 of them in fact, and it's a bit of an important number, and we can have a bit of a chat about that in a moment. The other critical thing that we need is a load bank, and it's basically just a big heating element. You put voltage and current through it, and as long as it doesn't overheat and melt down because of our squirrel cage fan, it's going to blow heat back out. So with the load bank, what's happening is when everything comes through as electrical potential energy, it's then converted into heat. And any physicist will tell you that it's not actually the bonk that's the worst, lowest form of energy. It's actually heat, heat loss, heat death. It's very hard to recover anything from heat. You need to add more energy in to convert heat into something else. So that's what our load bank's doing there. And probably the primary area where the energy is being expended in the unit. However, there is energy being expended in the coils, in some magnetism, in the flywheel itself as well. When you touch that flywheel, it does get quite warm post-ride, particularly if you've been doing a race on Swift. You've been maybe doing 500 watts for the last few minutes of a race. That's going to be pretty warm to the touch. So, and that's still energy. It's your energy. It's not energy that the power pack or that's coming out of the wall. That's you. That's you making that heat. So you feel it in your body, and you're also feeling it generated within the Neo. A few questions about the overall cooling of a Neo package. I'm not really going to cover too much of that here. Having a look at the magnets, the neodymium spec, I don't know too much more about them. I don't have any test equipment, and you'll find out how much test equipment I don't have by some of the estimations that I'm going to make moving forward through this presentation. But effectively, you can see they're marked sequentially with positives and negatives. So they are a flipped array, and there's a different number to the number of poles. I mentioned before there were 30 poles on this unit. I can't remember if there's 31 or 29 magnets, but there is an odd number of magnets from matching pairs in this. And it's probably just having a look at our stators and coils again. Even though there's no moving parts in this, there's still internal resistance that we do have to worry about. The load bank for this unit, for example, is 5.6 ohms of resistance. Think about an ohm of resistance kind of like riding through water or having to ride through honey. The higher the number, the harder it is to push through with electrical energy. The phases on each of the windings on this are also 0.5 of an ohm, so very low resistance. It's only 1/10 the resistance of the load bank. So the idea is that they're trying to not heat up the coils as much. They're trying to let all the current dissipate through all the wires, and then dump all that energy into the load bank to distribute it more effectively there. Having a look at the poles a little bit closer as well. There's 30 poles, and they're in a matched set of 10. So every third pole is going to be hooked up to each other. So this pole here, 1, 2, 3, is going to have a copper winding with him, and then that winding is going to go 1, 2, and then 3 to that one there. This is more commonly referred to as an AC motor or an AC generator. A lot of the time, depending on what sort of electrical equipment that you're looking at, it's either going to be single phase in Australia 50 hertz with 4 poles, sometimes 2 poles, not very common, or it'll be 3-phase 6-pole. And literally there'll just be 1, 2, 3 sets of poles, and each opposing each other, which makes those 6 poles in a 3-phase AC motor. The reason that they've more than likely set the Neo up like this is the Neo doesn't know what's about to hit it, whether you're about to drop a wattage bomb, whether you're going to do a slow leisurely cycle, and it doesn't know what the speed that you're going to do is. The speed, obviously, for this can be anywhere from a 3 or 4 kilometre an hour trundle all the way up to 60, 70, 80 kilometres an hour. Some people getting over, 100 down some of the courses on Zwift in, negative 20% descents and things like that. So the flywheel speed that you're seeing on the outside of a Neo is the same as it would be for your 700C road bike tyre. So there's no difference there. So just having a look in a planar diagram, exactly what's happening in our electrical system here. Keep in mind, as I've said before, don't have many tools, make the best of what we've got, and you'd be surprised in the engineering field how often people use Microsoft Paint to get the job done. So effectively, if we consider this as one of our magnets, and these are our poles, in our matched set of poles, our magnet's going to be traveling roughly like this, past all of our poles, then continuing on. Keep in mind there's a conveyor belt of other magnets. There's a negative magnet. So we can actually look at that and say he's going to be negative, like we discussed before. If I can find my paint bucket. So now I've got positive, negative, positive. Having a look again. As our flywheel spins, our 2 magnets are traversing the poles. And we can just imagine that this is almost like a train line or a conveyor belt at the moment. Don't worry if it's round or not. We'll cover that in a moment. The purple here is indicating a magnetic force. So as these magnets are going across, there's a magnetic force that's pushing its way into the pole. It's then generating some magnetism, which is reacting with our copper windings, and then that's making electrical current. When a little train of magnets moves, the arrow actually reverses and it pulls magnetic force back out of the pole. So this arrow would be going in the other direction, and then AC current still flows, but it starts flowing equally and opposite back in the other direction as well. So having a bit more of a look at what's happening here now from a magnetism point of view, we obviously can't see magnetism. There are some funny things you can do with iron filings and other things to visualize what's happening with magnetism. I'm not going to do that because everything's going to get messed up on the trainer, but effectively what's happening is there's like a rising hill of magnetism that's coming out of each one of the poles there. And we can imagine this like almost like a pile of snow that's either coming out of the ground or that we're trying to push along. Now, here's my representation of a bulldozer. This is you. And with your bulldozer, you're going to use the scraper on the front to start ploughing snow. So it's almost like you're constantly moving forward and trying to climb this hill. So you're always going to have an equal and opposite force from the magnetism pushing back against you or the magnets that you're attached to. And that's the magnetism in black here is obviously generated from the poles. Now, Nikola Tesla came up with this idea back in his time, well over 100 years ago now, and he came up with 3-phase power and the rotational motion of electrical motors. A few different styles of electrical motors out there. There's delta configuration, star configuration, 3-phase electrical motors, synchronous, asynchronous, inductance, reluctance motors, and a whole bunch of others. I am not actually sure what style generator and 3-phase arrangement we have here, but more or less we can start making the same assumptions about exactly what's actually happening inside with some basic mathematics. Now, just a quick recap on the control board for the Tacx Neo. Split up into sort of four main areas, really. First area here is our power inlet. That's where our power pack plugs into, and the voltages are then split up around this area and distributed to where they need to be used around the unit. As I've said before, 3.8 volt capacitor there, which powers primarily the two IC chips here. Area number 2 is the communications area, where your Bluetooth Net Plus come in and out from. Area number 3 is the digital processing area. That's basically making all the decisions about what your unit's doing and when it needs to do it. Area 4 with its MOSFETs. This is really where the business end of what's going on happens. All of our voltage and current is coming through this area, and there's a big aluminium heatsink on there to dissipate some of the stray current and stray heat that's generated from this. Some MOSFETs up there, probably for the fans, and some other I/O pins up in that area. So having a look, you can see that the capacitors and the MOSFETs are all matched in pairs, gated like this. So that 7th, I believe, is for the road feel. And what's happening there is when this is bypassing current into our load bank at certain voltages and certain currents, this is misfiring just a little bit, which is sort of making a bit of a clunking sensation in the unit. A very, very clever design from Tacx on that. Now, having a close look at the capacitors that we have here, 470 nanofarad and 100 volt, what appear to be electrolytic capacitors. Quite a large capacitor. Now, the job of these capacitors isn't to absorb all that much energy. If you outpace the system and speed up the flywheel too quickly, there is a little bit of a cushion where they will absorb some of the voltage and some of the potential energy that you're putting out. But it's only until the system can catch up and the digital processing realizes that it needs to compensate for the extra effort that you're exerting on the system. What the capacitors are going to do is hold a level of voltage that's equivalent to the voltage that the magnets are creating in the stators. And it's going to be in sync with what's going on, but just a little bit ahead. So it's always going to feel like you're trying to continually fight and climb that hill that we spoke about just before. The aluminium bar at the top where the MOSFETs are, that's effectively where all the power is going to come in to these pins before it gets redirected to the load bank. The voltage is going to match, as I've said, what the capacitors are storing, and it won't allow any of that high current, the few amps. I think some of the calculations that we'll see later will be tens of amps, which is a huge amount of current. It's nothing to sneeze at. It's going to bypass that current into the load bank, and we'll do a calculation on that at the very end to be able to prove that we are actually seeing the power that we are. But in terms of voltage, we're only talking about the potential of energy. We're not really talking about absolute energy or anything like that. So in terms of all the energy that you produce, it's kept on the upper side of this board, and all the controlling is done at the bottom of this board just by putting in a little bit of voltage and current to act as the gatekeeper, as you will. So just to try and put in perspective what this is trying to do here, normally with electric motors, particularly three-phase motors, we'll use something called a variable speed drive, a VSD, and with a control input from some sort of logic device or governing device, we'll effectively charge up some resistors and capacitors and provide that to the motor in a controlled way to lock it at a certain speed, which will provide rotational torque on the other end that you can use for different things. This is a little bit different because what we're trying to do is drain away some potential energy out of a system. And you don't know what the potential energy that's about to come into the system is, because it changes. The flywheel speed changes, your effort changes, you might go for a sprint, changing gears. It all becomes pretty complicated. So you've got to be able to sense what's going on and compensate for it pretty rapidly. Something that, arguably Tacx have done pretty well. A lot of people don't mind after you get used to it, the feeling of riding one of these units is not too bad. So in a real world application, where would we see this? Like, where would you use it every day? And after thinking about it for a while, I couldn't find anything except for maybe a wind turbine. The big wind generation turbines that you might see on the roadside or out in the oceans. And the way that it's similar to what we're doing here on the Tacx Neo is on the control side, you don't know what's about to come in. You don't know how strong the wind's going to blow. If you've got wind gusts, the wind might drop away. So what you have to do with a wind turbine is put a little bit of voltage in just to excite the stator in the motor so it can start just slowly spinning over and starting to build up some electrical energy in the system. And then when the wind really hits those blades and they can get the blades pitched correctly, then they can really start driving more voltage into it, and therefore voltage and current. They can start drawing a lot more power out of your wind turbines. Now, before we get started too much with the mathematical side of things, we need to set up a few test conditions that we can start comparing our figures to real-world approximations. Now, the best thing I've been able to find on this is a couple of websites here. I'll put all the links down in the video description so you can scroll through everything that I'm going to present today. But cycling power and speed, pretty simple one. As the kilometres per hour rise, the energy that we need to expend to make that bike goes faster is a bit of a runaway freight train. Like, we can't, most people could ride for 20 kilometres an hour all day, every day. And as you see here at the bottom of the screen, it's about 60 watts of power that you need to do that. However, to go at 50 kilometres an hour, you really need to hold 600 watts in this particular example. So it's a bit of a losing proposition. Obviously, another 5 k's an hour on top of that. There ain't too many people amongst us that are going to hold 55 k's an hour on a flat road with no tailwind for very long. Now, this is also assuming there's no wind, as it says here. There's no, it's flat road. There's nothing impeding you. So this is perfect real world. More akin to what you might actually find on Zwift, funny enough. Some of the same approximations that we can make here, just put in a few things for myself. So 20 kilometers an hour, we'll say that we're riding on the drops. Of course, every chain on a Tacx Neo is new and well oiled, I'm sure. Probably not, but zero wind, 0 grade, 0 elevation. And at 20 kilometers an hour, this is saying that it's around 60 watts. Having a look here. Funny enough, this one's around 60 watts as well. So that's a pretty good indication that around 20 kilometers an hour, whatever calculation that we come up with, we need to be seeing that as the power that our unit's seeing. So now we've covered off approximately where we're going with our power. What we can do is have a look at the time it takes for our flywheel to do certain things. And it's basically the time it takes for it to get to its next matching pole, where the rising voltage and rising current will match the magnet coming and inducing magnetic flux and some voltage because of that as well. So if we have a look, the time it takes for a magnet to go from one pole to the other is 0.066 seconds at a virtual 15 kilometers an hour. And then it's a simple calculation from there. We say it's whatever that cell is at the top times 3, because it has to do it 3 times. Because we're in match sets of 10, it makes sense that the revolutions per second is just divided by 10 basically at that point. And then we can see the frequency as well. So how frequent is it that our magnets are traversing the poles? Now, you'll just have to bear with me from this point onwards in the content that I'm putting forward. I'm definitely not an expert here. I know enough to be dangerous, and I keep saying this over and over again. But some of the basic principles hold true. So we'll have a bit of a look at approximately what's going on here. With those 100-volt caps, at 470 nanofarads, at a certain frequency, we can start to determine what sort of a resistive force they can provide to our circuit here. Keep in mind, capacitors at a constant voltage do nothing. They will have no current coming in or coming out. Everything will just bypass straight by them. But our magnets are constantly creating magnetic flux and magnetic voltage. So we need these capacitors to effectively match what that voltage is. So there's going to be a little bit of peak and trough there. And a quick look at capacitive reactance and why it's important in our circuit. Our capacitors are sitting sort of in line as a bit of a fence or a barrier to stop some of that high current from racing back across the board to the other control areas. Obviously, we're talking about microelectronics with tiny wires. So, you know, in terms of the large power outputs, we don't want anything coming back past those resistors, those capacitors. But what we can do is use a calculation to effectively figure out when the frequency and the voltage is at a certain point, there must be so much current racing past the other side of those capacitors, and we'll use that in a calculation a bit later on. Now, the formula that we're going to use is XC is 1 over 2 pi of the frequency and the capacitance. The capacitance in farads, of course, frequency in hertz. Now, definitely feel free to go look up far better explanations than I can provide in how this is all derived. But we're just going to plug some numbers in and see what happens. Now, the way that our capacitors are actually doing their job is by sitting in a voltage range. Now, this is a scale of effectively 0 to, let's just call it 100% voltage charge. It doesn't matter whether it's 100% voltage or 100 volts or 1,000 volts or between 0 and 1 volt. It's just whatever we're seeing versus something else. Now, at this point, like me, electricity is very lazy. It wants to take the path of least resistance. So if you've got an empty bucket or an empty capacitor, for example, it's very easy just to dump as much into it as quickly as you want. It looks like an open circuit. It's a short circuit. So you've got the potential here in this charging curve when we're down at 0 volts to dump in massive amounts of current. 100% of your current can come into this thing. But obviously we don't want that. And we want to bypass all of this energy that you're expending into a Tacx Neo straight into the load bank. And that's the idea. We want to eject that out the back as heat. So we need to add a little bit of a control voltage to build that fence. Or another way to think of it would be, let's put a big hill in the way, or like I said before, like a building. If you want to go to the top floor of a building at the 50th floor, if you had to go around that building, you wouldn't go to the 50th floor, then come back down. You're probably going to walk around the outside or find a different way to get past. And the same thing's true here. We're going to charge our capacitor up to a certain point. Now, it's not on this curve. It's just 100% of what we want to hold that capacitor at to begin with. So if we want to hold our 100-volt capacitors at 50 volts, we can do it. If we want to hold our capacitors at 100 volts, we can also do that. or 1 volt or anywhere in between. All we've got to do is pre-charge those capacitors to hold that voltage. Now, when we're at 100% of our charge, the current that's coming in and out of our system is 0. So our current must be going somewhere else. So it's actually getting bypassed to that load bank like I'm talking about. So now that we understand how the capacitors are acting as that barrier and redirecting the current away and into the load bank from how the magnets and the poles are creating it, it's time to have a bit of a think about how this is going to be monitored and read in our system. Now, a couple of different ways it could be done, and I'm sure that there's circuitry in there to do it. You can measure the voltage and the current. You can measure some, maybe some temperature. You could measure a whole bunch of things. The simplest way is probably to do with measuring the voltage and a little bit of ripple in the system. And believe me, Tacx's algorithm to be able to operate these things is vastly more complicated and nuanced than what I'll cover here. But I'll give you a bit of a flavour of how they've probably got started in development of this. So instead of creating an electric charge, in this case, just keep in mind, this is just a diagram I quickly found on the internet, so it's not the exact one that I want to use, but we can put our imagination hats on again. Instead of generating a current, sending it to another coil and measuring how much magnetism we have, we don't really care about magnetism at all. So let's just assume that coil 2 here is our magnet, and it's creating some of this magnetic current or magnetic flux that's oscillating around inside our system. When that starts to energize these coils at a certain voltage, and we know that we can match that voltage in the capacitors, well, we know that there's resistance that we can determine or that we've already pre-calculated. We know that there therefore must be a certain amount of current at a certain amount of RPM, and we can measure the voltage. So the processing unit starts to make some pretty accurate determinations about what exactly is going on inside the unit. Again, you don't have to offset it too much if you can calculate the current and you can calculate the voltage accurately. In that case, you don't even need temperature offsets. You can just do a straight calculation of voltage and current equals power. So now, all this being said, the way that our traditional power meters are going to differ from everything else is they're much more akin to a set of kitchen scales or bathroom scales. You need to make sure from time to time that everything's zeroed out. And you can also get a little bit of drift either over time, the metal fatigues, heat does affect them. So there's offsets as well for those things for a strain gauge, but it's not potentially as laborious in some of the calculation that you need to do to pull the final figure out. But there is drift over time, which is a bit of a problem because power is just really force over time, and you can consider distance and a few other things. And if you're out of sync on your time, then everything starts to get a little bit complicated. I'm not going to go down that road just now. However, if you always know what your voltage and current is, as Tacx have done, you can do away with all that. And the way that Tacx have gotten away from having to zero and offset their machine is because everything's pre-programmed with, I suppose you'd be able to call it it's an offset value or a multiplier where it knows exactly the power that they tested at the factory and what the discrepancy was. So when they say that their power is plus or minus 1%, you don't have to zero the unit. It knows. It's just measuring that voltage and that current at that single point wherever it is on the board. So there is no drift. Voltage and current is what it is. Occasionally the coils might heat up and do something a bit weird. The magnetism might change a little bit, but we don't have to worry about that for our example, the processing chip is figuring all that out. But it's important to note that's why this is a matched set. The load bank resistance that I've measured on the unit that you've seen me tearing down is 5.6 ohms. And in each phase, in each of those coils on the poles, it's 0.5 of an ohm resistance, which is very, very low. Like, these are low resistance numbers. And that's so some of the current that we're going to calculate a little bit later on is going to go and dissipate really rapidly in those areas. Not so much in the poles. We want it to bypass the poles and not heat up too much there, but we do want it to heat up in the load bank. Now, the other thing that we need to have a quick chat about is the relationship between amps, volts, ohms, and overall power output. As you can see here with this colourful chart, there's a few different ways that you can calculate things if you're missing some information. Now, I haven't got an oscilloscope, so I don't know what the frequency is. In some cases, I don't know what the voltage is. I don't know if it's AC or DC voltage. And I don't know what some of my currents are within this. To determine what some of the currents are, I would actually need to break the circuit and put a multimeter in line. And for a whole bunch of reasons, that's just a little bit too difficult. So we might calculate the potential current that we might be seeing in the load bank at the end. And it might be right, it might not be, but again, all approximations. But what we're going to focus on here is mainly just our power at the moment. Again, anything with I in this case is amps or current. So I don't know what that is. So we're going to be able to use to find power, or to derive power, V as voltage and R as resistance, because those are two figures that we actually do know. So I started to think about how this system's preconditioning itself, getting ready to go. And that 25 volts that I've calculated, it's kind of down here in that 15 kilometer range. So I have a feeling that the peak voltage that it needs to supply, with the plus or minus, which is half of our peak to peak, it's only very low. It's very low control voltage, and that's kind of why you get a little bit of slipping, because you can really accelerate those magnets pretty hard and pretty quick in a sprint condition, at least from a standstill. When you've got a bit of inertia in the system to begin with, you're up in the higher gears, you've got a bit more wheel speed, not such a problem. And that'll make a little bit more sense a little bit later on when you see how the calculations are performed. Looking at a 20 kilometer an hour column here, though, everything scales pretty linearly. We keep adding more voltage, and as the frequency changes on our calculation here with the impedance or the reactance on that capacitor, we can say, well, okay, if the voltage is scaling in a pretty linear way, and here's our scale here, for every 2.5 kilometers, I'm adding 2.4 volts of electricity into those capacitor banks. In each phase, I'm starting to get, for here, 18.4 watts of power. Obviously, it's a three-phase system, so we can multiply that by 3. And we get 55.3 total watts of energy that this system is able to handle. Now, that's actually pretty similar to the chart that I showed you before, and we'll cross-check that later. So back to our website, and here, roughly around 30 kilometers an hour, it's saying 153 watts of power that would be needed to generate that outcome. So not quite right, but there's other things going on within the units, sort of internal resistance and things like that we're not calculating. So in terms of an approximation, that's pretty good. We can have a look here as well. For 40 kilometers an hour, roughly 326 watts of effort is required. Having a look at our other site, 30 kilometers an hour again, roughly the same. So in that 150 range watts, and for 40 kilometers an hour of effort, about 315 watts of energy. So now that we've got a bit of an understanding about how we can ramp up voltage on one side of our capacitors and use it to deflect some current around towards the heat bank in relation to the frequency of the flywheel, we can go full circle and we can start saying, well, what are some other load points that we know of? Now, keep in mind that linear scale is, there's a bit of fudge factor, there's some offsets and calibration that I've spoken about, and some of the steps between voltages go up in a little bit of a lumpy way. But if we keep coming across on our chart here, I've gotten to 50 kilometers an hour, and all the calculations are there, and I'll put the link in there so you can sanity check what I've done. But just having a look at the bottom of the chart, we would need approximately, as I have estimated, 64.1 volts of power, which again, it's pretty linear steps, does jump up a little bit as we start going up this way. And to go at 50 kilometers an hour, we would actually need pretty close to 600 watts of energy to match that voltage that we would dump in, or vice versa. If we had 600 watts of power, we would need 64 volts of power in our in those large capacitors to sort of offset what we're trying to throw against this thing. Now, what if we take it to the extreme? What if on this virtual flat road with no crosswinds, we did 70 kilometers an hour or 80 kilometers an hour? Well, I moved the formulas out and I cross-checked it again. Now, sorry, it's starting to rain. I'm in the shed, so you might be getting some feedback on the mic. But up around the 80 kilometer an hour mark, we see that to sustain that effort, you would need 2,200 watts of power, which is an extreme amount of energy. Only the best of the best sprinters can output that level of effort, even if it's only for a fraction of a second. But if you go to Tacx's website and have a look at their Neo specifications, 2,200 watts is what they say the unit can handle. And if you remember correctly before, we said that those capacitors can hold 100 volts of charge. And sure enough, cross-checking everything, when those capacitors are up in the high 90s, it will actually hold 2,000 watts of charge. So this gives me some level of confidence that I've actually picked the right numbers here to start with. Now, I did have a quick theory on why I think off-board cadence sensors may be a little bit better for these units. Obviously, the first generation Neo didn't have any of the onboard cadence sensors, but it could still figure out how you were able to, or what speed you were pedaling at. And it had to do with the digital signal processing on the chip. It could figure out with like pattern recognition, basically, every time there was a little bit more power coming in versus another part of the pedal stroke. Some wizardry, some mathematics happen. It was able to derive that. But the problem is, once you changed a gear or once you decided to get up and go for a sprint, the unit might be able to adjust the resistance, but to actually achieve the calculation, it had to take a moment to re-establish basically a synchronization to where it was, particularly if you went from the little ring to the big ring without changing anything else. All of a sudden, people were reporting 4 or 5 second delays in some of the first generation Neos being able to figure out what had just happened and recalculate an accurate power figure. Now, that goes along with some of the telltales that we've seen on the circuit board in terms of the original board having sense written on one of the inputs that was never plugged in. Now, I think that has to do with them abandoning the idea of a cadence sensor on the first generation, but then bringing it back in to kind of improve that responsiveness on the second generation units. Obviously, they've got their problems, different topic, but I would be interested to see if you took the the cadence sensing off the unit, took the responsibility off the unit via Ant Plus maybe, and an on-bike cadence sensor reporting exactly what the crank speed was doing to the Neo, then it can do the calculations. I suspect if that's the case, what's going to happen is when you hit the gear change, it will notice that the wheel speed might not change, but the crank speed did. It'll notice pretty quickly in that case that something's out of sync, and then start to recalculate a lot faster than it otherwise would have. Now, just for sanity's sake, even some of these low currents here at reasonably low voltage, they're high figures. Like this is why I keep saying to people, you shouldn't really be opening these units. Um, the potential voltage can be high, not that the capacitors should hold any of that charge longer term. But this unit, as you can see, can hold anything up to 20 amps of current that you're putting through it, just in a load bank. So if anything shorts that out, that's a huge amount of energy that's really going to ramp through that system and cause a lot of damage and destruction to anything that it comes in contact with. So once again, public service announcement, probably not the best idea to open these units. If you can find someone to repair them, great. If not, well, come to the community and we'll see if we can help you. Now, that's pretty much all from me at the moment from the teardown on the Neo. Happy to hear your thoughts. If you've got more questions, please ask. And keep asking questions yourself. Like, I hope some of this will help people with their training potentially. So, yeah, anyway, keep having a quarantine, everyone. And hopefully we'll see you all on the road pretty soon.